You might think this robot tentacle is just a soft, floppy thing, but it's actually being used as a camera gimbal, and not the kind that just sits there. You move the handle, it follows. You stop, it locks in place, perfectly steady. Even more impressive, pour cold water on it, drop heavy objects on it, try to shake it, and the camera barely jitters at all. Anyone who knows their stuff might already be raising an eyebrow. This just doesn't seem possible, because the thing driving it is a famously slow, extremely laggy material, shape memory alloy, SMA, a material that's basically born with a slowpoke gene. How on earth did they tame it into a tentacle that responds in milliseconds, like a perfectly obedient gimbal? In today's video, in just 5 minutes, we'll break down the breakthrough from Tsinghua University, the active cooling SMA-driven soft tentacle. Let's start with a question that's often overlooked. Are shape memory alloys really slow? Well, not exactly. Heating an SMA is actually quite fast. What really slows the system down is cooling. Think of it like boiling water. It heats up quickly, but waiting for it to cool naturally can take forever. In traditional control systems, this cooling process is basically ignored. The controller has no way to step in. The core idea of this paper is refreshingly simple. If cooling is the bottleneck, why not control it too? So the team does 2 things. First, they introduce active air cooling. Second, they explicitly include the cooling process in the control model, instead of treating it as an uncontrollable disturbance. From that point on, the SMA is no longer just heated up and wait. It becomes a fully controllable actuator, able to both heat up and cool down quickly. To make this work, the team builds a thermal model that's classic, but absolutely essential. At its core, this model answers just one question. Where does the heat in the SMA come from, and where does it go? When current flows through the SMA, it generates heat. That's the input. At the same time, air carries heat away through convection. That's the output. The balance between these two determines whether the temperature rises or falls. Here's the really clever part. The model includes a parameter called the convective heat transfer coefficient. In traditional SMA systems, this value is basically fixed. But in this system, it can be actively adjusted by controlling the airflow. And that changes everything. Cooling speed is no longer just a natural phenomenon. It becomes a control variable. Think of it like this. Before, it was summer with no air conditioning. You just endured the heat. Now, the controller decides how strong the AC should blow. Next, let's look at the control design itself. This soft tentacle is driven by 3 SMA springs, evenly spaced around its body. Instead of directly controlling how hot each spring should get, the team takes a more intuitive approach. They describe the motion using just 2 variables. One tells you how much the tentacle bends, the bending angle. The other tells you which direction it bends, the bending direction. It's very much like controlling a camera gimbal. You don't think about how much each motor rotates. You just say, tilt a bit, turn this way. The direction command goes through a distributor, which automatically converts it into different heating and cooling commands for the 3 SMA springs. With temperature feedback and posture feedback added in, the whole system becomes a fully closed-loop controller. Now, the most convincing proof comes from the experiments. In one key test, the team commands the tentacle to hold a 45-degree bend, and then continuously adds water into a cup at the tip, increasing the load over time. The result is striking. Even as the water is added little by little, the bending angle stays very close to the target, with only tiny fluctuations. Next, they apply a sudden 50-gram impact load. You can see the angle get knocked off for a moment, but the oscillation quickly dies down, and the tentacle snaps back to 45 degrees. Finally, the total load at the tip is increased to nearly 185 grams. Even then, the system remains stable, without losing control. This demonstrates something important. Cooling in the loop control isn't just fast, it's genuinely robust to disturbances. Finally, the team performs a very intuitive demonstration. They mount a camera at the tip of the tentacle and use a handle to control it remotely, turning the soft tentacle into a tripod-like gimbal. Wherever the handle moves, the tentacle bends accordingly, keeping the camera always pointed at the target. To sum up, this paper isn't just making minor tweaks. It's the first time the cooling process of shape memory alloys has been formally brought into the control loop. This turns SMA from a slow, laggy material into a fully controllable actuator. By using a control structure that decouples direction and magnitude, the soft tentacle gains the precise gimbal-like handling for the first time. Add in a series of load tests, impact experiments, and remote control demonstrations, and it's clear this system isn't just impressive to look at, it actually works. If previous SMA soft robots felt more like lab demos, this work clearly marks a step into real engineering systems.
If you enjoyed this, don't forget to like and subscribe so you won't miss more amazing robotics.